Nucleophilic substitution has three types of reaction. So one is with OH, nucleophilic substitution with OH, another one is KCN, and the last one is going to be ammonia. So for OH, when you have the reaction with sodium hydroxide, we do not have ethanol over there, so it's just going to be sodium hydroxide in aqueous form. So when you have the sodium hydroxide in aqueous form, the halogenoalkanes, okay, whatever halogenoalkanes that you have, they are going to be converted into alcohol. So the halogen is going to be substituted by the OH and it's going to be converted into alcohol. Now most of you will get confused in this part where the reaction of halogenoalkanes with silver nitrate solution. Now silver nitrate solution, when they react with the halogenoalkane, they do not react directly. They will react in form of the aqueous. It means the solution is in aqueous form. The aqueous contains water. Silver nitrate contains water. Water is going to be the nucleophile that will actually help to break down the halogenoalkane. It means substitution will happen because of the presence of water. And this is a breaking down of water using water. So we call it as hydrolysis reaction. And this hydrolysis reaction is quite similar with the reaction with sodium hydroxide in aqueous form. But the difference is it's quite slow. The reaction is quite slow. The product that we will get is still the same. It's going to be alcohol. Okay, still going to be alcohol with some side products. But it's going to be slow because the water molecule is a neutral molecule. Therefore, they are a weaker nucleophile if you compare to OH minus nucleophile over here because of the charge. So the reaction is going to happen quite slow, and do remember that both of these reaction, actually all the three reactions, you can classify them as they are going to be heated under reflux. You need to know what is the meaning of heated under reflux. Heated under reflux, basically you are going to heat a volatile solution without evaporating it. So you are going to actually heat it up, and because of the presence of condenser, it is going to cool down the temperature, and then the vapor can actually condense and fall back into the container, and then it will be reheated again and again until you get what you want. So this is going to be heated under reflux. And do remember halogenoalkanes, they are quite volatile. Now for the second reaction is going to be with reaction with KCN. The reaction with KCN is going to be ethanolic. It means with the presence of ethanol with the presence of alcohol. Do remember our first reaction, they do not have ethanol. It's just going to be sodium hydroxide aqueous. But KCN must be in ethanol. Even the third reaction, ammonia, must be in ethanol as well. And for KCN, the reaction is going to be heated under reflux, and you are going to get a product that is going to be having an extra carbon. And I mentioned about this in chemical synthesis. If you want to have a product with extra carbon, we can actually use this reaction, which is going to be KCN. KCN will help to actually add the carbon into the chemical compound. So the nucleophile over here, take note, it's not going to be the KCN directly, it's going to be the CN minus is going to be the nucleophile. The nucleophile for the first reaction is going to be OH minus. The nucleophile for the first reaction involving silver nitrate is going to be water. And before I forget, okay, the reaction after you get the alcohol, since you have the silver nitrate will react further. If you have the halogen, the X, if you have Cl, you are going to get silver chloride. If the X is going to be Br, you are going to get silver bromide. If this X is going to be I, you are going to get silver iodide. Take note that they will have a solid precipitate over there. So solid precipitate, each of them, they have their own colors. So the silver chloride, the color is going to be white. The silver bromide, the color is going to be cream, and silver iodide, the color is going to be yellow. Now, if you move on, the reaction involving ammonia, it must be in ethanol condition and it must be in excess. The reason why we have it in excess is we do not want to have a formation of multiple products, because when you do nucleophilic substitution, the halogenoalkanes is going to be, the halogen is going to be substituted by NH2, not NH3 will not go inside directly. So you are going to get RNH2, which is going to be amine. We call it as amine, and then the one of the hydrogen will come out, and then it will actually react with the halogen, so you will get HX. Then we go to the elimination step. Elimination step is almost similar with our first reaction, which is going to be the reaction with sodium hydroxide. But now, okay, the earlier one we do not use ethanol, but now we are going to use ethanol. It means this sodium hydroxide, now when you heat it under reflux with the presence of ethanol, you are going to get elimination reaction. So how the reaction actually works, basically if you have H and then if you have the Cl, okay, the rest you leave it like that. So this H and Cl, they will come out, okay, they will come out. Let's say if we are using sodium hydroxide, for example. So what's going to happen is they are not going to form HCl directly. Okay, the Cl will join with Na, so they will give you NaCl. The H will join with OH, they will give you H2O. And this one, once the H and Cl goes away, you are going to get this alkene. For the nucleophilic substitution, we have two mechanisms. So the mechanism is going to be SN1 and SN2. Now, if you look at the number of SN1 and SN2, one tells us that there is one reactant at the slow step or the rate determining step, and 2 tells us there are two reactants at the slow step or rate determining step. We also need to know that SN1, since it's going to be one reactant, it involves the formation of carbocation. And since we are talking about carbocation, we are going to talk about tertiary halogenoalkane, because tertiary halogenoalkane will form a tertiary carbocation, and this tertiary carbocation is much more stable compared to secondary and primary carbocation. Therefore, tertiary halogenoalkanes tends to form tertiary carbocation and they tend to follow SN1. So this is a very easy way to memorize this. Now for SN2, they cannot actually form carbocation, therefore they will form the intermediate. And since they cannot form carbocation, they must be primary halogenoalkane. It means they will be forming, if they want to form the carbocation, they will be forming primary carbocation, which is not favored in this case. So this is going to be a rough difference between SN1 and SN2 mechanism. So if you actually look at SN1, let's say I have actually one example. Let's say if you have this halogenoalkane, it's going to be a tertiary halogenoalkane. You can see this is going to be 1R group, 2R group and 3R group. This is going to be a tertiary halogenoalkane. It's going to actually react with sodium hydroxide. It's going to be in aqueous form, heated under reflux and without the presence of alcohol. So what we are going to have. So the moment when you see here SN1, okay, you need to remember anything that is involving the tertiary halogenoalkane, they are going to actually form a carbocation. So carbocation over here, okay, if you look over here, that they are going to actually have only one reactant at the rate determining step. So I'm just going to start with only this reactant. Now this reactant, what is going to happen first is going to be Cl is much more electronegative than carbon, so they will withdraw the electron towards itself and it is going to form a partial negative and a partial positive over there. So you do not need to actually put the OH minus over there, okay, because this is going to be SN1 mechanism. A tertiary carbocation will be formed, so you do not need to put the OH over there at the slow step. So what is going to happen over here is there is going to be a formation of tertiary carbocation. So I'll just draw the tertiary carbocation. So put like that, and then there is going to be a fission that happen. If you pay attention to what I said, it's supposed to be, in my previous lesson I mentioned that this is going to be heterolytic fission. You are going to get a Cl minus over there, and now the OH, okay, that we have, the nucleophile, they will start to come in and they will actually start to attack the carbocation, and they will start to form bonds. So this reaction is going to be fast, so you are going to get this molecule. So if you look at the SN2, okay, SN2, I have actually drawn a primary halogenoalkane over there. So this is going to be the only one R group that is attached to the carbon, attached to the halogen. So if you want to react with sodium hydroxide, okay, same situation, still aqueous form, heated under reflux without the presence of alcohol, okay, or without the presence of ethanol, what will happen? So this one, we know that since it's going to be 2, the number 2 tells us the slow step involves 2 reactants. So I have written the 2 reactants over there. So the nucleophile will be present in the slow step or some kind of slow step. For SN2, take note, okay, you do not need to mention there is a slow step, there is a fast step. No need to mention. So you just need to just show, okay, this is going to be the first step and this is going to be some kind of slow step where the 2 reactants are going to be involved. So what is going to happen? Similar reaction, Cl is going to be much more electronegative, so they will withdraw the electron and then you have delta positive. But at the same time, okay, this OH minus, they will start to attack the carbon. So the nucleophile, the OH minus, will actually attack the carbon over there of the halogenoalkane, and they are going to form intermediate. So if you want to draw a nice diagram, I will suggest you to draw something like this. This bond is going to be broken, so you can actually put a dotted line over here, Cl, and if you want your diagram to look nice, you can actually put the bond that will be formed as OH over here, and then you just show this 3 just like this, and then you just put in hydrogen, CH3, H, and hydrogen, CH3 and H. You just put it over there. So this is what we call as intermediate. The next step is basically to get the bond, which is going to be CH, CH3, H, and then the OH. Okay, you can put the OH anywhere, doesn't matter. Okay, then plus the Cl minus. So you are going to get the alcohol, but the steps are different. The step for the first one is going to be, you are going to get the carbocation. Okay, for SN1 you will get the carbocation, but now for SN2 you are going to get intermediate. And that's the summary of the lesson.